Activated sludge is often described as a biological treatment process. That is true, but it is incomplete. In a working plant, the real challenge is not to memorize a single number. The challenge is to see a changing system, distinguish a useful signal from noise, and decide what must be checked before anyone changes a control setting. This episode follows that diagnostic chain. We will move from the incoming wastewater to the aeration basin, then to secondary clarification and solids return. At each point, we will separate four things: what can be observed, what it may mean, what other evidence is needed, and who is authorized to act. That distinction protects plant performance, people, and the receiving environment. No universal aeration rate, return sludge setting, wasting rate, chemical dose, or effluent response will be prescribed here. Those decisions depend on the plant, its design, permit, influent, equipment, laboratory method, and operating authority. The aim is better questions, not a remote operating recipe. Begin with a physical map. Wastewater arrives with variable flow, solids, organic material, nutrients, and possible industrial or storm-related changes. Preliminary and primary steps may remove material before biological treatment. The activated sludge stage then gives microorganisms an environment in which they can transform soluble and suspended pollutants, while secondary clarification separates biological solids from treated water. This sequence is useful because it reveals two connected jobs. The aeration basin must support biological conversion. The secondary clarifier must separate and return solids reliably. When performance is weak, the visible symptom may appear in one location, while the initiating cause lies upstream, downstream, or in the relationship between the two. The first discipline is therefore simple. Do not start with a favorite explanation. Start by drawing the actual plant path, including bypasses, recycle lines, equalization, chemical addition points, aeration zones, secondary clarifiers, return activated sludge, waste activated sludge, and the sampling locations that are truly available. A plant is not a still diagram. It is a story over time. Flow may rise sharply. Load may change without a large change in flow. Temperature can shift. Equipment can go in and out of service. A rain event, an industrial discharge, a pumping change, or a maintenance action can alter the conditions seen by the biology and the clarifier. That is why one sample or one visual observation is rarely enough to explain a problem. A useful diagnostic record combines time-stamped observations. It asks what changed first, what changed next, and which measurements move together. Process control guidance treats observation, testing, interpretation, and adjustment as a connected operating cycle rather than isolated tasks. In this episode, every question follows that sequence. Observe the condition, confirm the data, compare it with the plant's own normal pattern, check competing explanations, escalate only through the plant's approved decision process. The first label is observation. For example, the final effluent looks different. The blanket appears higher than usual. A blower is unavailable, or ammonia results have changed. An observation is not yet a cause. The second label is interpretation. A high blanket might relate to solids loading, settling behavior, hydraulics, return capacity, equipment condition, sampling timing, or something else. An interpretation must remain a hypothesis until it is checked. The third label is confirmation. This may involve laboratory quality control, repeat sampling, instrument checks, flow review, field notes, operator rounds, or an approved calculation. The fourth label is authorized response. Only after the plant's own procedures, limits, and responsible personnel are engaged does an operating adjustment become a decision. This framework may sound cautious. It is cautious by design. Activated sludge is a living and hydraulic system, and a confident but unsupported change can make a weak situation worse. Before diagnosing biology, understand what the plant is receiving. Influent information is not merely a dashboard decoration. It frames the workload placed on treatment. Review the time pattern of flow, known industrial contributions, weather, upstream storage, pump operation, and any deviation from the plant's normal profile. Then check the quality of the information. Was the sample representative?
Were preservation and analysis methods appropriate? Did the flow totalizer, sampler, or laboratory process show an issue? If the data chain is uncertain, mark it as uncertain. A number with unknown quality should not be promoted into an operating conclusion. This does not mean waiting for perfect information. It means declaring confidence honestly. A plant team can respond to a credible risk while continuing to verify its cause. That is very different from treating a single unexplained reading as proof. The aeration basin is where biological conversion and oxygen transfer meet mixing, hydraulics, temperature, and solids inventory. Air systems deliver oxygen, but the process control question is broader. Is the basin providing the conditions intended by the plant's design and operating strategy? An operator's round should connect what is seen and heard with what is measured. Are blowers available? Are air headers, valves, diffusers, mixers, and instrumentation functioning as expected? Are basin patterns consistent with normal conditions? Are there unusual dead zones, foam patterns, odors, turbulence, or alarms? Each clue is useful, but none should be treated as a diagnosis on its own. The goal is a coherent picture. Instrument data, field observations, maintenance status, and laboratory results should be able to tell the same general story. When they do not, the disagreement itself becomes a valuable troubleshooting clue. Dissolved oxygen is commonly monitored because it helps show the relationship between biological demand and oxygen transfer conditions. Yet a dissolved oxygen reading should not become an automatic instruction. The value depends on where and when it was measured, calibration quality, basin configuration, mixing, temperature, loading, and the plant's treatment objectives. A sound question is not simply, what number should we see? A stronger question is, does this measurement at this location and time fit the current process story? Compare readings across relevant zones if the plant is designed for zones. Review trends rather than a single snapshot. Confirm instrument maintenance and calibration status. Then relate the information to treatment results and equipment condition. This approach avoids two errors: ignoring a meaningful low or high trend and overcorrecting based on a number that does not represent the process.
The microorganisms in activated sludge need appropriate conditions, time, contact, and separation to carry out their role. For process control, it is useful to think of the biomass as an inventory that is continuously affected by influent load, solids wasting, return flows, solids loss, and settling behavior. Terms such as mixed liquor concentration, sludge age, solids retention, food to microorganism relationships, and settleability are ways to describe that inventory. They are not magic dials. Each depends on sampling, flow, laboratory methods, assumptions, and the configuration of the actual plant. When a calculated value changes, ask what physically changed. Did flow change? Did measured solids change? Did wasting change? Did return flow change? Did a clarifier lose solids? Did an instrument or laboratory result change? The calculation is a prompt for investigation, not a substitute for it. The secondary clarifier is not an afterthought. It is where treated water and biological solids must separate in a dependable way. If solids settle and return as intended, the system can retain the biomass required for biological treatment. If separation becomes unreliable, both effluent quality and the solids inventory can be affected. Observe the clarifier deliberately. Look for the plant's approved indicators of surface condition, solids carryover, scum, hydraulic distribution, rake or scraper operation, sludge withdrawal, return paths, and blanket information. Pair field observation with operating data. Is the condition isolated to one clarifier? Did it follow an equipment change? Is the return system available? Is there a hydraulic or solids loading explanation that needs confirmation? The central lesson is that a biological symptom and a clarification symptom can be linked, but neither should be assumed to cause the other without evidence. When treatment performance is questioned, use a first diagnostic branch. Is the main issue more consistent with conversion, separation, or an incomplete evidence record? Conversion refers to the biological and chemical transformation occurring through the treatment process. Separation refers to retaining and removing solids in the clarifier and related solids handling paths. This branch is not a final answer.
It organizes the next evidence. If solids are visibly escaping, the clarifier path deserves attention. If laboratory indicators suggest a changed biological response while clarification appears stable, the aeration and influid context may deserve attention. If data disagree, the priority may be sampling and instrument verification rather than immediate process adjustment. Good teams can hold more than one hypothesis at once. The objective is to narrow uncertainty methodically, not to win an argument quickly. Suppose an indicator changes during a mooring shift. Before proposing a change, place it on a timeline. What did the value do over the previous samples? What did flow do? What changed in weather, industrial input, chemical supply, maintenance, or equipment availability? Was there a sampling or laboratory exception? Did the clarifier appearance change at the same time? Trend review converts isolated data into context. It also reveals whether a condition is worsening, recovering, oscillating, or simply outside a normal range for one measurement cycle. A disciplined trend chart should show the source, time basis, units, and known reliability limits. A graph without context can be as misleading as a single number. This is why operating logs matter. A short, factual note about a blower alarm, a pump outage, a storm, a chemical delivery, or a change in sampling can become essential evidence later.
An effective daily board is not necessarily complex. It might combine influent flow and load indicators, key aeration and clarification observations, laboratory trends, equipment availability, alarms, maintenance events, and the operator's concise narrative. The point is to make relationships visible. Use clear labels. Separate measured values from comments. Identify missing data instead of silently replacing it. Show when a sample was collected and when it was analyzed. Indicate whether a value comes from an online instrument, a grab sample, a composite sample, or an approved calculation. The board should support a conversation between operations, maintenance, laboratory staff, management, and engineering. It should not become a competition over whose number is correct. When sources conflict, the team should agree on the next verification step and record why it was chosen. Consider a hypothetical case. The final effluent appears less clear than usual. The wrong response is to announce a cause immediately. The first response is to define the observation. Which outfall, which time, which weather condition, which clarifier, and which supporting measurements are involved. Is the change confirmed by samples or only by one visual observation? Next, check the separation pathway. Review clarifier surface condition, solids carryover indicators, return and wasting system status, hydraulic changes, equipment alarms, and the reliability of blanket or solids measurements. In parallel, check whether a sudden influent event, upstream upset, or sampling issue could be contributing. Only then should the approved plant response process decide whether an intervention is needed. The episode's message is not do nothing. It is act on verified plant-specific evidence. Now consider a different hypothetical case. An ammonia result changes from its normal pattern. The result may matter, but it must be placed in context. Verify the sample, method, reporting basis, and timing. Review temperature and other available biological process indicators. Check whether aeration equipment, mixing, flow, load, chemicals, or operational configuration changed. The purpose is to distinguish a process trend from a data problem, and to identify whether multiple observations support the same concern. Training materials emphasize using several kinds of observation and test information when troubleshooting, rather than relying on one isolated result. If the risk is credible, the next action belongs within the plant's response plan, permit context, and supervisory structure. The video must never replace that escalation path with a generic command. Conflicting data are common. An online instrument may indicate one condition, while a laboratory result suggests another. A clarifier may look unusual, while key solids results remain near the plant's expected range. A calculation may change, even though no physical change is obvious. When information conflicts, resist the urge to average it mentally. Make the disagreement visible. Check instrument calibration and maintenance records. Repeat or confirm sampling through approved methods. Review time alignment.
Were all data points collected from the same operating period? Check units, transcription, and calculation inputs. The disagreement may reveal a real process transition. It may also reveal a measurement problem. Either finding improves control. What creates risk is hiding uncertainty behind a single tidy narrative.
Suppose a blower, return pump, sludge handling component, sensor, or clarifier mechanism has limited availability. The immediate task is not to improvise outside the safety system. The immediate task is to understand the treatment consequence, maintain safe operation, communicate the limitation, and follow the approved contingency process. Maintenance and operations should share the same process story. What is unavailable? For how long? Which treatment zone or clarifier is affected? What redundancy exists? Which observations and measurements need closer monitoring? Who must be informed? What limits are set by the facility's operating procedures and permit? This is where a well-kept diagnostic board becomes practical. It provides a common record for handover, repair planning, management communication, and subsequent review. The best process control framework fails if information is trapped in one shift, one notebook, or one person's memory. Handover must preserve the story. What was observed? What was verified? What is uncertain? What action was taken? Who authorized it? And what should be checked next? Use direct language. Avoid shorthand that a new team member cannot interpret. Record the time zone and operating period. Identify the affected unit. State whether an item is an observation, a test result, an interpretation, or an action. Where possible, link the note to the controlled procedure or work order. This discipline supports continuity. It also makes later engineering review more useful because the team can reconstruct the decision chain rather than guessing from disconnected data points. No performance issue justifies bypassing safety controls. Aeration, clarification, pumping, electrical equipment, chemical handling, biological exposure, confined spaces, and working near water all require facility-specific controls. The correct operating response may include stopping work, isolating equipment, calling qualified support, or following emergency procedures. For this reason, the video will show safety as a decision gate, not as generic background footage. Before a field check or maintenance action, the visual story will ask, is the task authorized? Are hazards identified? Are isolation and access requirements met? And is competent supervision present? If not, the correct next step is escalation. Technical confidence is not a substitute for a safe system of work. The safest decision can also be the most professional process control decision. Aeration can be a major operational focus because air delivery, mixing, biological demand, equipment condition, and energy use interact. But energy optimization cannot be separated from effluent performance, equipment reliability, safety, and permit obligations. A change that reduces power while weakening treatment is not automatically an improvement. Frame energy as a controlled comparison. Define the operating period, influent conditions, treatment result, equipment status, and measurement basis. Then review energy data alongside process data. Do not compare unlike days without acknowledging the difference in flow, load, temperature, or configuration. The best narrative is not use less air. It is use verified data, plant intent, and authorized controls to balance treatment objectives with reliable operation. That language is more accurate and more transferable across facilities. Here is the episode's reusable decision chain. First, observe the condition and record time, location, and source. Second, verify the measurement or observation using approved checks. Third, contextualize it against flow, load, weather, equipment status, and recent operational history. Fourth, separate hypotheses: conversion, separation, hydraulics, measurement, or another defined pathway. Fifth, escalate within the facility's authority structure when a risk, uncertainty, or required response is identified. Sixth, act only through approved controls. Seventh, review the outcome and document what changed. This chain does not eliminate complexity. It makes complexity manageable and auditable. Notice that the chain does not begin with a knob, a valve, or a dosage. It begins with evidence. That is the habit this episode is designed to reinforce. A strong review meeting is not a presentation of certainty. It is a structured conversation. One person may summarize the influent and weather context. Another may report aeration basin observations and equipment status. Laboratory staff may explain samples, methods, and trend confidence. Clarifier observations and solids handling information can then be reviewed alongside treatment results. The group should identify what is known, what is uncertain, and which question matters most next. If an operating change is considered, the responsible person should confirm the applicable procedure, risk controls, authority, and monitoring plan. Afterward, the outcome should be reviewed rather than assumed. This model turns operational knowledge into a shared engineering asset. It also prevents a plant from becoming dependent on one individual's unwritten intuition. The finished Water Atlas episode will make the reasoning visible. Each 10-second beat will show one idea: a system map, a measurement boundary, a time-stamped trend, a clarifier observation, an evidence card, a decision branch, a safety gate, or a handover note. Diagrams will be original and intentionally schematic. They will not imitate another organization's slides, footage, or graphics. Every case will be explicitly hypothetical. Every source-derived concept will have a corresponding reference in the episode package. Every site-specific decision will be framed as a question for the responsible facility team. Arabic subtitles will translate the intended meaning in clear modern standard Arabic, while preserving the scope limits rather than turning educational content into an operating instruction. Activated sludge process control is not the art of finding one perfect number. It is the discipline of connecting evidence, uncertainty, people, equipment, biology,